digital yang digunakan untuk mengelola leadership development journey dan juga memberikan kemudahan kepada peserta dalam memilih pembelajaran pasca leadership program. PLN Corporate University mempersembahkan Smile, Sistem Monitoring Implementasi Pembelajaran Leadership atau Kepemimpinan. Smile adalah sistem monitoring dan evaluasi berbasis web untuk memonitor journey dari peserta sebelum, saat, dan pasca pembelajaran leadership. Smile juga merupakan platform untuk memelihara soft kompetensi atau future kompetensi untuk para leader dan talent di PLN Group. Aplikasi Smile dapat diakses lebih dari 50.000 anggota dari PLN Group melalui internet di smile.pln-pusdiklat.co.id. Untuk saat ini, Smile dapat diakses menggunakan username dengan nomor induk pegawai atau NIPEG dan ke depan akan dikembangkan menggunakan account corporate atau melalui single login IMPLN. Aplikasi Smile mempunyai beberapa fitur, yaitu satu account untuk semua role, antara lain peserta, mentor, penguji, manajemen, dan pembimbing. Work plan dan action plan, atau mentoring dan coaching. Telah terhubung dengan aplikasi yang lain untuk menampilkan hasil asesmen peserta pembelajaran leadership, khususnya level manajemen atas dan manajemen menengah. Peserta dapat memilih pengembangan soft kompetensi yang disesuaikan dengan kebutuhannya berdasarkan rekomendasi dari hasil asesmen. Monitoring dan reporting. Pelaksanaan program dapat dengan mudah dimonitor dan menghasilkan laporan data pelaksanaan untuk manajemen dengan data yang real-time. Project Library, kumpulan data program atau proyek yang sudah dilaksanakan. Katalog pembelajaran pasca leadership program untuk memelihara soft kompetensi yang dapat dipilih sesuai kebutuhan masing-masing leaders. Smile akan terus dikembangkan dalam bentuk Divisi Talent Development dan SDM Unit dapat mengusulkan dan tracking peserta secara live. Peserta dapat memilih modul pembelajaran yang semakin beragam, baik secara virtual classroom maupun self-paced learning yang direkomendasikan oleh machine learning. Untuk informasi lebih lanjut, dapat menghubungi pada kontak berikut. PLN Corpus Smile, the new age of learning. Dengan berkembangnya teknologi di industri 4.0, menyebabkan kita dapat mengakses berbagai macam hal di dunia digital dengan mudah. Hal tersebut mengakibatkan munculnya format-format dan kebiasaan baru dalam mengakses konten pembelajaran. Di sisi lain, PLN juga menyusun strategi transformasi dengan 4 fokus utama, yaitu Green, Innovative, Customer Focus, dan Lean. Maka dari itu, PLN Corporate University melihat hal ini sebagai tantangan untuk bertransformasi secara digital dalam proses pembelajaran. Untuk menjawab tantangan tersebut, PLN Corporate University meluncurkan beberapa produk digital learning untuk memenuhi kebutuhan belajar secara auditory dan visual. PLN Corporate University mempersembahkan LISA atau Learning Solution Assistant. LISA merupakan sebuah aplikasi chatbot pembelajaran berbasis artificial intelligence yang dapat diakses setiap saat melalui WhatsApp. Karena menggunakan machine learning, LISA akan semakin pintar seiring dengan banyaknya interaksi antara pengguna dan LISA. Apabila LISA belum mampu menjawab pertanyaan, pengguna akan dihubungkan langsung dengan subject matter expert. Sehingga jika ada pertanyaan yang sama seperti sebelumnya, LISA akan dapat secara langsung menjawab pertanyaan tersebut. Layanan LISA terintegrasi dengan aplikasi WhatsApp dan dapat diakses di nomor berikut. Setelah menyimpan nomor LISA di WhatsApp, PLNers dapat berinteraksi dengan LISA melalui chat WhatsApp. Langkah pertama, ketik sapaan kepada LISA, seperti Hai dan Halo untuk memulai percakapan. Lalu, LISA akan membimbing PLNers untuk memasukkan nama PLNers. Nama yang dimasukkan akan secara otomatis tersimpan oleh LISA. Setelah itu, LISA akan membimbing PLNers untuk mengakses materi pembelajaran dengan memberikan kode akses sesuai daftar judul pembelajaran, kode pokok pembelajaran atau modul, dan selanjutnya kode sub pokok bahasan. PLNers hanya perlu mengetik kode tersebut untuk dapat mengakses materi-materi yang ada. Setelah selesai mengetik kode-kode tersebut, PLNers akan diberikan akses download materi sesuai yang diinginkan PLNers. Melalui Lisa, pengguna juga bisa melakukan self-assessment melalui fitur quiz dan post-test yang tersedia di setiap judul pembelajaran. Selain itu, Lisa juga mempunyai fitur Q&A dan FAQ. Lisa akan membimbing PLNers untuk mengetik fitur-fitur tersebut jika diperlukan PLNers. Lisa akan terus dikembangkan dalam bentuk tersedia materi untuk setiap profesi. Terintegrasi dengan media pembelajaran lainnya baik visual, auditory, maupun kinestetik. Machine learning yang semakin pintar seiring berjalannya waktu sebagai teman belajar. Untuk informasi lebih lanjut, dapat menghubungi pada kontak berikut. Lisa, the new age of learning.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Before we start our event today, to the committee and attendants, please listen intently to Indonesia Raya, Mars PLN, and Harmna PLN.
Majulah negeriku, majulah PLN untuk selamanya. Jayalah PLN untuk selamanya.
Good afternoon, ladies and gentlemen. Also, good morning to the guests coming from Ireland. Please allow me to introduce myself. My name is Farika Himawati from BDPLN Persero Pusdiklat as the Master of Ceremony today. May we all blessed with great health, and let me give you one pantun. Menjaga listrik malam dan siang, dari PLTA Cirata sampai PLTA Tulis. Selamat datang Bapak dan Ibu semua dalam Power System Sharing Series. Welcome to the fourth Power System Sharing Series entitled Smart Defense Camp to Maintain Power System Stability. Ladies and gentlemen, before we start the fourth Power System Sharing Series, please allow me to announce you the rule of this event. Please set your identity of company, then following with your name. Please turn on your video and turn off your audio while attending the webinar. Don't forget to apply the virtual background that we have shared in the chat box. Don't forget to apply presence list in the link that we have provided also in the chat box. And for Q&A answer, please mention your question based on the format name /unit/company and the question. And the last is to set your Zoom application in speaker view mode in order to enjoy the spotlight. The webinar is also facilitated with a language interpreter feature from Global Bahasa. There will be a detailed explanation by Global Bahasa. To the Global Bahasa, the stage is yours.
Oke, thank you. Selamat siang Bapak Ibu. Izinkan kami dari Bahasa Global untuk membacakan panduan cara menggunakan fitur penerjemahan. Good afternoon, ladies and gentlemen. Allow us from Bahasa Global to present the user guide how to use the interpretation feature. Berikut panduan cara mengaktifkan fitur penerjemahan pada aplikasi Zoom apabila Bapak atau Ibu menggunakan laptop atau PC. Pada bagian pojok kanan bawah akan terdapat lambang bola dunia. Mohon untuk diklik language interpretation dan memilih bahasa yang Bapak atau Ibu ingin dengarkan. Mohon tidak perlu mute original audio dan tidak perlu pindah channel saat berbicara. Ladies and gentlemen, if you are accessing the Zoom using a laptop or PC, simultaneous interpretation services are available. You can go to the bottom right of your screen. There you will find globe icon or language interpretation button. Click it and select the language that you wish to listen. We recommend you to not mute original audio. And if you would like to speak, you don't have to turn off the interpretation button as well. Apabila Bapak atau Ibu mengakses meeting kali ini menggunakan mobile phone, fitur penerjemahan secara simultan juga tersedia. Bila Bapak atau Ibu ke pojok kanan bawah, akan ada 3 titik. Jika diklik, akan ada language interpretation. Lalu klik dan pilih bahasa yang Bapak atau Ibu ingin dengarkan. Dan tidak perlu mute original audio. Dan terakhir, jangan lupa klik dan bila sudah selesai. Ladies and gentlemen, if you are accessing the Zoom using a mobile phone, simultaneous interpretation services are available. You can go to the bottom right of your screen. There you will find 3 dots. Click it and click language interpretation. And select the language that you wish to listen. We also recommend you to not mute original audio. And don't forget to click done when you have selected. Thank you and have a productive webinar. Terima kasih.
Thank you so much, Global Bahasa, for your explanation. And please allow me to greet a special welcome to representative of Global Power System Transformation Team, Mr. Mark McGranan from EPRI, to the Honorable Business Regional Director of Sumatra Kalimantan that will be represented by the EVP Transmission, Mr. Nurwahyu Dinianto, the host of Fourth Power System Sharing Series, as well as Executive Vice President PET Center of Excellence, Mr. Heri Nugraha, Mr. Daniel Elia Wardana, General Manager from PLN UIKL Kalimantan, as well as our speaker today, and also our guest speaker from Electric Power Research Institute and ERGRID, and to the distinguished EVP from Distribution Air Sumatera Kalimantan Regional, Mr. Jeffrey Rosiadi, EVP Transmission Regional Sulawesi, Maluku, Papua, dan Nusa Tenggara, Mr. Warsono, EVP PR, Mr. Suwarno, General Manager PLN Pusertif, Mr. Septa Hamid, General Manager UID Lampung, Mr. Sindu Putra, General Manager UIW Kalbar, Mr. Ari Dartomo, General Manager UIW Aceh Abdul Muklis, and also all the distinguished EVP and General Manager that already attends this meeting. Distinguished guests, also the rest of this webinar participant, and all PLN officials who are also watching this event through Zoom meetings or YouTube channel. Once again, good afternoon and welcome to the biggest event of Power System Sharing Series in PD PLN Persero. Before we start our agenda, let's pray together. Pray begin. Finish. To ignite our spirit, let's do these yells together. I will write the yell in the first sentence, and please, I ask you all to the guests and the distinguished EVP, General Manager, and also the editors to answer my first sentence of yell. Semangat pagi.
Pagi.
PLN berakhlak Anda terbaik. Thank you for sharing in this Monday afternoon. And ladies and gentlemen, regarding to the EODB, electricity has become the one of crucial indicator to determine a business and economy. The index of stability will greatly impact the demands of doing business in Indonesia. In the coming years, the digital era and strong global commitments to the use of cleaner and renewable energy will influence the demands and consumption patterns of electricity users. As the leading company in electricity, PD PLN Persero strongly commit to initiate new opportunities and innovations to be beneficial not only for the company, but also for the economic and more than 70 million electricity consumers throughout the country. As you can see in this agenda as one of them, please take a look for this company profile video.
This is where our journey begins. Power plant, transmission line, We do operating. We do maintaining. Creating energy for you. Bringing alive in a split second. We delivered power from here to here. And yet, you probably give us no more thought than a flick of a switch. Every day we take new steps, open new paths and deep roads. Addressing the future as the subject of present, making our daily life easy. Powered by PLN.
Okay, ladies and gentlemen, for the first agenda today, please welcome to the House of Ford Power System Sharing Series, Vice President of PD PLN Persero PET Center of Excellence, Mr. Heri Nugraha, to deliver the welcoming remark.
Terima kasih. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good afternoon, ladies and gentlemen. Good morning in Dublin time. The Honorable Mr. Muhammad Iqbal Nur, the Region Business Director of Sumatra and Kalimantan of PLN, who is represented by Mr. Nur Wahyu Dinianto, the Executive Vice President of Transmission of Sumatra and Kalimantan Regional Business. The Honorable Mr. Mark McGrahanot, representative of Electric Power Research Institute in Dublin, Ireland. The Honorable Mr. Sean McQuinness, the Technical Executive of Transmission and Distribution Grid Protection Research from the Electric Power Research Institute, Dublin, Ireland. The Honorable Mr. Ray Doley, the Head of System Integrity from the Air Grid of Dublin, Ireland. The Honorable Mr. Daniel Eliawardana, the General Manager of Generation and Transmission of Kalimantan System. All Director, EVPs, General Manager from PLN and subsidiaries, and all of you, all distinguished guests. Welcome to the first webinar of the PLN GPST Power System Sharing Series. Let us praise God Almighty for the opportunity we have to conduct this valuable seminar. Dear Sir and Madam, the surface level requirement is providing electricity has been evolving over the years. As we recall, many years ago, providing 24 and 7 days electricity in many areas in Indonesia was a great challenge. Although availability is still an issue in the few places today, the challenges has been shifted into delivering reliability and quality to the customer economically with great concern in using green energy resources. Dear Sir and Madam, as we all know, in providing good electricity to the customer, we need reliable power system and individual component in them. We see that our power system also evolved to be more complex over the years. Issues like stability rise recently, not just because the system itself grows in capacity, but also the likelihood of increasing the contribution of the renewable energy in the future could change the nature of the power system itself. Consequently, the way of we protect the power system also need info from a traditional to modern way, as this become the main topic in this fourth GPST webinar. Dear Sir and Madam, we also thankful today because our honorable speakers from the IPRI, the 8th grade from Dublin and PLN will share this knowledge and experience about smart defense scheme to protect the stability of the power system. We encourage all the audience to participate actively and having a great time during this webinar. Thank you to the team who prepared this occasion from the PLN Corporate University and PLN P2B. Welcome and enjoy the seminar. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Shalom, Om Santi Santi Om, Namo Buddhaya, Salam Kebajikan. Thank you very much.
Thank you very much, Mr. Heri Nugraha, for this warm welcoming speech. Now also we have Mr. Haryanto WS, the Business Regional Jawa Madura Bali Director. Good morning and good afternoon, Mr. Haryanto WS.
Selamat datang Pak Haryanto, terima kasih atas kehadirannya.
To the distinguished participants, ladies and gentlemen, moving to the next agenda, please welcome Business Regional Director Sumatra and Kalimantan of PT PLN Persero, Mr. Muhammad Iqbal Nur, and for this time would be represented by Mr. Nur Wahyu Junianto to deliver the opening remarks. You are kindly requested.
Terima kasih, Mbak Fadika. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Thank you very much to Mr. Heri Nugraha from PLN Center of Excellence as our host for today's Power System Sharing Series for webinar. And thank you very much to Board of Directors, Pak Haryanto, have attended in this webinar this afternoon. First of all, I will let me give my warm welcome to distinguished speaker, the Honorable Chief Operating Officer of Airgrid Airline. Good afternoon, Mr. Ray Doyle, and good afternoon, Mr. San Genes McGuinness, as Transmission and Distribution Protection Research Program Manager of EPRI from Ireland. And good afternoon to Mr. Daniel Eliawardana as General Manager PLN Unit Indo, Pembangkitan dan Penyaluran Kalimantan. And also, I also would like to thank and welcome all the executive of power system operators and institutions who are members of the Global Power System Transformation or GPST Consortium. Thank you very much to all GM and EVP from PLN that have attending attended in this webinar, sorry. And good afternoon to all webinars participants who watch via the YouTube channel and also through the Zoom meeting. On this occasion, allow me to represent the Regional Business Director of Sumatra and Kalimantan, Mr. Muhammad Iqbal Nur, to deliver our webinar's opening remarks. We take the topic of the Smart Defense Scheme to maintain power system stability. Mr. Iqbal conveyed his warm greeting to all participants and apologize for not being able to attend this webinar due to another agenda. Distinguished ladies and gentlemen, this is the fourth webinar initiated by PLN and Global Power System Transformation Consortium, focusing on support to power system operators with advanced low-emission solution. This webinar is an effort of the cooperation to provide knowledge to the power system operators among the partner countries required to support the global energy transition. As we know, the need of electricity has increased tremendously in recent years. Our customer expectation 10 years ago were relatively low compared to present. They may have been quite satisfied with a condition in which electricity as it is. However, with the ever-changing and fast development in technological devices, customers nowadays need a good quality of electricity to 24 hours to support their daily needs. At the exact moment, Indonesia is aiming to become an industrial country, and PLN is expected to assist industrialization and become a part of the industrialization process by increasing investment in electrical power system to achieve reliable and high quality electrical power. Since April 2020, PLN has launched a transformation program with 4 aspirations: green, lean, innovative, and customer focus. This transformation shifts PLN strategy from previously supply-driven to demand-driven. One of the breakthroughs, also called the anti-blackout program, emphasized with our CEO's message to provide excellent services and security of supply for electricity consumers. In order to mitigate this risk of system blackout, in Sumatra and Kalimantan region has made several efforts, such as performance improvement to main equipment, protection system, SCADA, and defense scheme, infrastructure development, and competency improvement for human resources, as well as transmission system network strengthening. In line the increasingly complex power grid, a smart defense scheme system is urgently needed to dynamically perform calculation based on real-time system condition to maintain the system stability and also reduce the impact of disturbance. We often call it the Spatial Protection Scheme or Dynamic Defense Scheme. Distinguished ladies and gentlemen, today we will listen the presentation from several experts in their respective field, especially regarding Smart Defense Scheme and its application to maintain power system stability. Hopefully, the discussion that take place can be beneficial to all of us. Here, I'm officially opening this webinar. I would like to deliver my appreciation to all speakers from EPRI, EarthGrid, and PLN for all of participation. My special appreciation also delivered to the cooperation in GPST Consortium for the willingness to provide capacity building to the power system operation engineer in partner countries and for your contribution to make this webinar to happen. Finally, on behalf of PLN Board of Directors, I would like to declare the webinar to be open. Thank you and have a great discussion on the Power System Sharing Series 4 webinar. Stay safe and stay healthy. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you, Mr. Nur Wahyu, for the wonderful opening remarks. Okay, ladies and gentlemen, before we move to the main agenda, since COVID-19 pandemic is still spreading all around the world, unfortunately, we couldn't organize this event offline. So, allow us to have a documentation by doing the virtual photo session together. Firstly, please kindly open your video and give two thumbs up like this. And your best smile today. I know this is Monday afternoon, but please give us the best smile. Keep your best pose and let us capture all the screenshot about 10 seconds. So I will count it down from the 10, 9, 8, 7, 6, 4, 3, 2, 1, and thank you, and let's have a big applause for this Monday afternoon. Okay, before we start the presentation session today, please kindly visit our attendance list on the link that has been mentioned in our chat box and YouTube channel. The participant can also write down your question on the chat box for the Q&A session later. Since we have all the speaker and moderator here for the first session in our webinar room today, please allow me to introduce today's young, smart, and talented man. His name is Mr. Haryadi Aji. He was graduated from Electrical Engineering Institute Teknologi Bandung in 2009 and pursued his master degree of Electrical Power Engineering in Delft University of Technology, the Netherlands, in 2016. And for now, he is working as Assistant Manager of Transmission System Operation and Planning at PLN Persero Unit Indo P2B. We are glad to invite Mr. Haryadi Aji as the moderator. Good afternoon, Mr. Haryadi Aji. I hope you are good today.
Yes, good afternoon, Mbak Farika.
Okay.
Yes, I'm
And
good,
now,
thank you.
the stage is yours.
Okay. Thank you, Mbak Farika. Good afternoon, ladies and gentlemen. The Honorable Director of PLN, Board of Director and Commissioners, PLN's Regional Business Director of Sumatera Kalimantan, Pak Muhammad Iqbal Nur, represented to EVP Transmisi, Pak Nur Wahyu Dinianto, Regional Business Director of Jawa Madura Bali, Pak Haryanto, Senior EVP of PLN's COE, Pak Heri Nugraha, and all PLN leaders. Also, good morning, Mr. Mark McGranagan, and GPST expert speakers, and all of audiences in this webinar. Welcome again to this fourth Power System Sharing Series entitled Smart Defense Scheme to Maintain Power System Stability. Please let me introduce myself. I am Haryadi Aji from PLN UI P2B Jawa Madura Bali, and I will be your moderator during this session. I'd like to send my gratitude to all of the participants, especially all the speakers that have joined this webinar and willing to share their knowledge with us. Thank you. Very soon, we are going to hear 3 presentations from each speaker. After 3 of our presenters finish their presentation, then we will have a Q&A session. All of the participants in this webinar are free to join this Q&A. You can ask some questions to the speakers by testing in the chat box in the Zoom meeting. Also access the link in the presence link in the chatting. And be spirited. The best question will be rewarded and announced at the end of this webinar. And don't worry, you can ask the question both in Bahasa or in English. So please don't hesitate to ask some question during the Q&A session. Besides, to see the audience comprehension about the material, we're going to have a fun quiz after this panel session, also with some rewards. It is worth a try, so please stay in this webinar until the end of the session. Ladies and gentlemen, before we go to the first speaker, let me bring you some burning question that we would like to find the answer in this session. Defense scheme implementation is very important to keep the system secure. Nowadays, with the development of technologies, the defense scheme is getting smarter, also with sophisticated technologies. So will that defense scheme technology will be reliable? What aspects that we have to keep in mind to make our system safer? Will these defense schemes matter? In the future power system with massive renewable energy penetration? Let's find the answer soon through our expert speakers. Let's go to our first speaker. He is Pak Daniel Elia Wardana, General Manager of PLN Pembangkitan dan Penyaluran Kalimantan. Ladies and gentlemen, let me briefly read the short biography of Pak Daniel. He is currently General Manager of PLN UIKL Kalimantan. He has a bachelor degree in electrical engineering from Institut Teknologi Surabaya and Magister Management from Sekolah Tinggi Manajemen PPM Jakarta. He has a lot of experience in power plant as electrical engineer, supervisor, and manager in Tanjung Priok combined cycle gas turbine power plant. Also in Adipala and Lontar coal-fired power plants. Then he was appointed as head of power generation division in PT Indonesia Power and power generation vice president in Sumatra region of PLN's head office. Pak Daniel, let me check with you now. Are you already here with us?
Okay, good afternoon, Pak Haryadi.
Okay, excellent. I can hear your sound very well. Terima kasih, Pak. Thank you for joining with us and to present this slide. Yeah. In this occasion, Pak Daniel will present about system protection scheme in Kalimantan. Without any longer waiting, Pak Daniel, you have 20 minutes to deliver the material. And I will remind you when the time remaining is 3 minutes left. And now the platform are yours.
Thank you, Pak Haryadi. Is it clear, my voice? Oke, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan salam sejahtera untuk kita semua. The Honorable BOD of PLN, Mr. Haryanto WS, the Honorable PLN Center of Excellence, represented by Mr. Heri Nugraha, the Honorable EVP of Transmission, Sumatera Kalimantan, Mr. Nurwahyu Dinianto, the Honorable Speakers, ED7, Mr. Sean McGuinness from EPRI Ireland, and Mr. Ray Doyle from Airgrid Ireland, the Honorable Executive of System Operators and Institutions who are members of GPST Consortium, distinguished participants, ladies and gentlemen, who attend this webinar either via Zoom meeting or via YouTube. Good afternoon for Indonesia time, good morning for Dublin time. On this occasion, I will share our experience in Kalimantan in implementing system protection scheme. Before start, I will read a poem, pantun in bahasa. Matahari pagi bersinar terang, jangan lupa berjemur agar badan tetap sehat. Hari ini hati terasa senang, berbagi di Power System Sharing Series 4.
Cakep.
Okay, next slide. Okay, today we have 5 agendas to be shared. The first is a summary of our experience. The second is an overview of power system in Kalimantan. Then I will briefly describe the philosophy of defense structure in power system and the working principle of SPS. The fourth is how we implemented SPS in Kalimantan. And the last, we will talk about the further development of SPS. Next. Okay, UIKL Kalimantan is an organization of PLN in power generation and transmission, established in 2018 to operate and maintain asset of PLN, power generation and transmission, in Kalimantan Island. More than 2,000 megawatt power generation, almost 7,000 kilometer circuit transmission line, 80 substation, including 150 power transformer. We operate and maintain. Besides that, we are also responsible for operation and maintenance of 26 isolated systems across Kalimantan Island. The highest peak load so far in Kalimantan reached 1,720 megawatt, achieved in the first week of June 2021. The main reason for implementing SPS in 2017 is to avoid blackout and immediately recover system to normal condition. And the SPS successfully prevents some blackouts that potentially occur following major system disturbance. After being installed in Katulistiwa grid, the SPS was also installed in the Mahakam and Barito subsystem, as well as in Bangkanai power plant. SPS is designed to work properly, adapting to the current system condition, to anticipate several possible events according to system requirement or network topology. To monitor the performance of SPS, we established Grafana-based dashboard system in PLN headquarters in Banjarbaru, South Kalimantan. In the future, we plan to install more SPS in Kalimantan, where 8 SPS in Mahakam subsystem and 7 SPS in Barito subsystem. Next. Next, I will explain the overview of Kalimantan system. Okay, on this slide, the following is a brief description of Kalimantan system, which consists of two major grid systems, the Katulistiwa in West Kalimantan and the interconnection system in South Kalimantan, Central Kalimantan, and East Kalimantan. Katulistiwa system has a total generation capacity of 700 megawatt with a peak load of 430 megawatt, while the interconnection system's total generation capacity of 1,604 megawatt with a peak load of 1,290 megawatt. The Katulistiwa system is interconnected with SESCO Sarawak grid system via 275 kV network. The supply from SESCO covers around 30 to 45% of the total load of Katulistiwa grid. Interconnection system consists of Mahakam subsystem in East Kalimantan and Barito subsystem in South Kalimantan and Central Kalimantan. The subsystems are connected via Tanjung Barikin line, which has maximum carrying capacity around 250 megawatt. Next. Next, we talk about the generation capacity, fuel mix, and load stacking in June 2021. The following graph, we can see that the highest peak load in 2021 occurred on June 4, 2021. In the Katulistiwa system, consists of 69% energy composition from the coal power plant, 23% supply from SESCO, and the rest was contributed by biodiesel and biomass fuel generators. Meanwhile, the peak load in the interconnection system also occurred on the same day, with the composition of energy from coal power plant at 80%, gas power plant contributing 17%, and the rest from renewable energy plants such as hydro and biogas. In general, primary energy in Kalimantan system are dominated by coal. Next, we discuss about the major causes of grid disturbance in Kalimantan. During the last 3 years, 80% of disturbances in Katulistiwa system are caused by kite wire, while for the interconnection system, almost 70% are caused by lightning and 20% by trees. The chart shows the number of disturbances for each transmission line, where the most frequent disturbances occur in Siantan Seiraya Line, Kalimantan Barat, in Pontianak. It is because kite flying is one of the local cultures. We are continuously working hard to minimize the disruption caused by this kite. Next. In the next agenda, I will explain more about the simplified defense structure or line of defense. Next. As we know, the defense structure or line of defense can be simplified into 3 stages. The first stage is prevention or planning. The second stage is supervision or action, while the last stage is the ultimate perils. These ultimate perils are corrective action to prevent system collapse or blackout and speed up the recovery process. SPS can be categorized into this stage. Next. According to CIGRE Task Force report, the System Protection Scheme or Remedial Action Scheme, originally called the Special Protection Scheme, is designed to detect abnormal system condition. It takes predetermined corrective action to maintain system integrity. From the block diagram on the screen, we can see that SPS gets input in electric variable, or we can call response-based SPS, or direct detection, or we call event-based SPS. These inputs will be processed to get what action will be taken. Next. Based on the Task Force CIGRE report on SPS in power network, there are various actions that can be taken according to the system requirement, of course. For Kalimantan, so far we have used several actions such as frequency load shedding and also generation rejection. Other actions are being studied for use in the future SPS in Kalimantan. Refer to system requirement. Next. Okay. Next agenda, we will explain about the implementation SPS in the Kalimantan system. Next. Okay. The installation of SPS began with a blackout in the Katulistiwa system in April 2017. At the time, the Singkawang-Bengkayang line transferred around 109 megawatt from Cisco, Malaysia, while the generation from PLN was only 96 megawatt. The disturbance on Singkawang-Bengkayang line caused the frequency system to drop quickly. Even though we have DFDT relay, it was unable to restore the frequency quickly, resulting in the blackout in the Katulistiwa system. From this incident, several stages were made in planning the SPS. The first stage is to study the initial system condition. We talk about the network topology, etc. The second stage is to analyze the possibilities that occur and their consequences. The third stage ensures that the SPS design met the requirement. And the last, of course, is what action to be taken if some of these possibilities occur. Following the same event in October 2017, same trips in Singkawang-Bengkayang, SPS can quickly return the system frequency to normal condition through precise load shedding, following the power transfer through the line before disturbance. So we can see on the chart on the right, after we install SPS, system can recover back to the normal immediately because the SPS can shed the amount megawatt or amount feeder meet to the power loss from transfer. Next. This is first SPS that we have already discussed, installed in Katulistiwa grid. There are system initial condition, we have contingencies, we have system response evaluation, and there are 4 action. We have a selected action for every contingencies. Next. How about the SPS hardware? The installation of SPS consists of 3 important parts. There are data acquisition, data process, and data execution. Starting from data acquisition, SPS retrieves data from SCADA to be transferred to the offline database server for feeder load data and line load. Then the data is processed on the SPS server, where the calculation process is carried out to obtain feeder data ready for load shedding. In addition, the calculated data is also sent to the web server to be displayed via the Grafana dashboard system. The feeder data ready for load shedding is sent to SPS hardware in the form of mini PC, plus an input-output module to prepare the feeder to be executed when a contingency occurs. When a contingency occurs, the SPS relay publisher will send trigger signal, a GOOS protocol, to the SPS relay subscriber to execute the feeder previously prepared by the SPS server. Next. How this system works. We can see on the slide, let's say 100 megawatt transfer from substation A to B. Every 10 seconds, the SPS server will perform calculation based on data from SCADA to ensure that the number of transfer is equal to the number of feeder loads that are ready for shedding. So this is a dynamic process. Every time is different, the calculation. The higher the transfer, the higher the target load to prepare for shedding. Let's say if transfer condition is 100 megawatt, several feeders will be selected with a total load approximately equal to 100 megawatt. Then the SPS server will send a ready signal to the selected target. When there is a disturbance that causes the transfer to become 0 megawatt, the SPS relay will send a GOOS signal which will initiate the shedding target that SPS has prepared to be tripped. Next. This is the second SPS in interconnection grid in Kalimantan. The first in interconnection, the second in Kalimantan. We can see on the screen that the most highly loaded area in the interconnection system is in South Kalimantan, while the power plant is mostly located in East Kalimantan. So that to meet the power demand, a transfer is required through Barikin Tanjung transmission line with a maximum power transfer up to 250 megawatt. Tanjung Barikin line is a backbone to transfer from North to South Kalimantan. If there is a disturbance on that line, it will cause several negative impacts to the Barito system. It can cause an overload on South Kalimantan side, resulting in steep decrease in frequency and voltage drop in Banjarmasin, leading to system collapse. That's why we need this. This is the third SPS, like in Tanjung Barikin scheme. Cempaka Barikin transmission line is also important power evacuation transmission line that needs to be installed with SPS because a fairly large power transfer past this transmission line. Even though we have looping circuit on Barikin Kayu Tangi, seberang Barito line, this scheme is still needed to maintain voltage security and overload security on Kayu Tangi seberang Barito line. Next. This is the fourth SPS in Kalimantan, different with before, a previous slide. We have different approach to keep the generator operating and avoid overspeed in Bangkanai Power Plant. The Tanjung Buntok Teweh line is radial network for the supply of Bangkanai Power Plant, while the load in that area is only 20 to 30 megawatt. So, if one of the section trips two lines, the Bangkanai, Power Plant Bangkanai will survive only with 20 to 30 megawatt. The scheme prepared is an engine trip by leaving 3 to 5 engines from 16 engine. And at the same time, we open one transmission line to ensure voltage security. Next.
Excuse me, Pak Daniel, you have 5 minutes left.
Okay, thank you. Next, one slide more. Yes. As explained in previous slide, SPS readiness can be monitored in real time through Grafana dashboard system in our office in Banjarmasin. The following picture is an example of condition in real time, where transfer load is 202 megawatt. We can see second circle. The active target is 201 megawatt. From the total load quota, 290 megawatt. The red color, we have many list of red color below, indicates the target feeder target that is ready to be executed if something happen in power transfer. This data is obtained in real time from the SCADA offline database server. Next. Distinguished participants, ladies and gentlemen, we have arrived at the final agenda. In this section, I will briefly explain the future development of SPS in Kalimantan. Next. The development of the system, such as additional substation, as well as increasing consumer load, will provide changes to Kalimantan interconnection system. The following are the result of our scanning for potential disturbances in Mahakam subsystem that have a major impact on the system. So we have already scanned the possibility 8 risks in the interconnection system. We will install 8 SPS development plans in the Mahakam subsystem with 6 schemes to overcome contingency constraint and 2 schemes for island operation scenario. Next. Like, yes, Barito subsystem. Like previous slide, the Barito subsystem, also we will install more 7 SPS development, focusing on operational constraint, voltage and frequency drop. Okay, next slide. Okay, for future development, this graph shows the SPS topology for development plan. The previous topology of the communication between the server and the SPS hardware in the subsystem used sharing a database, existing condition. Yeah. In order to improve cyber security, the communication line between the server, IED, Intelligent Electronic Devices, and SPS relays will use standard protocols of IEC 61850 and IEC 8705104. In addition, SPS server can also acquire data directly from RTU SAS with this new topology. We are currently in the process of procuring server and supporting equipment to improve the cyber security of the system. Next. Distinguished participants, ladies and gentlemen, that is all the information we can share in a very limited time regarding our experience in Kalimantan in implementing SPS. If there are further questions or discussion, please feel free to write down the question in the chat box or email for further explanation. Before back to Pak Haryadi, I will read again poem pantun in bahasa. Pergi ke laut memancing ikan, ikannya meloncat hingga daratan. Sekian sharing yang bisa kami bagikan. salam dari kami UIKL Kalimantan. Sekian, wassalamualaikum warahmatullahi wabarakatuh. Back to you, Pak Haryadi.
Thank you very much, Pak Daniel. Such an enlightening knowledge sharing about the brief system in Kalimantan and its special protection scheme there with very clear explanation. We understand that the scheme is equipped with the smart algorithm and it is very proved. Yeah. That's like the example, the disturbance of transmission lines between Kalimantan and Malaysia, and the SPS is working and is finally proven to stabilize the system. And I see that the SPS is developing to get better and better with the new scheme and also with the new technologies. That's why the Kalimantan's SPS is really special, yeah, especially for us in PLN. Thank you, Pak Daniel. Before we step to the next presentation, I would like to inform all of the audiences that the attendance link is now available in the chat box. Please fill the attendance form. And if you want to ask some questions, please type it in the same platform with the attendance link. There's a link in there. Or you can ask directly in the chat box of Zoom. Please add your name, your unit in PLN, and to whom do you want to ask the questions. The question will be selected and answered in the end of all presentations. Let me remind you that we will choose 3 best questions that will be rewarded, so stay in tune. Let's go to the next speaker. The second speaker will be Mr. Sean McGuinness. Ladies and gentlemen, I'd like to briefly read the short biography of Mr. Guinness. So Sean McGuinness is a program manager at the Electric Power Research Institute, or EPRI, in the Grid Operations and Planning Group of the Power Delivery and Utilization sector. He has graduated as Bachelor of Science of Engineering and Master of Science of Electrical Engineering from University College Cork, Ireland. He managed a number of EPRI projects in transmission and distribution protection areas, real-time operation tools, harmonic, transients, etc. He is also a principal investigator for major system disturbances all around the world. He is active member in IEEE Power Energy Society with multiple journal publications. I'd like to greet him. Good morning there in Ireland, Dublin. How are you, Mr. Guinness?
Thank you, and thank you for the opportunity to present today, and good afternoon to you all. Thank you for your kind introduction.
Yeah, thanks. The thanks is also mine and all of us. Okay, Mr. McGuinness, you have 25 minutes to deliver the material about smart defense scheme to maintain power system stability. And yeah, I will remind you when the remaining time is 3 minutes left. Without any further ado, now the time is yours.
Thank you. So today I'll be presenting, you can move to the next slide. You can move to the next slide if you wish. So today I'll be covering system integrity or system defense schemes. So typical applications, examples of schemes that are in service around the world. Operating experience where SPS or SIP schemes have failed and caused major disturbances. Some examples of good design practices and conclusions and future expectations for these technologies. So if you can go to the next slide. And you can go to the next slide again. And again. So one thing to note before we begin, there's many different terms used for these defense schemes, such as SPS, RAS, or system integrity protection schemes. Sometimes they're called system defense schemes, or sometimes they're given just local names. So we will use these terms across the presentation, but they mean slightly different things to different people. Just moving on to the next slide. So as mentioned by the previous speaker, these defense schemes, they're typically automatic grid protection schemes, and they're used to detect abnormal or predetermined system conditions. In contrast to most protection systems which detect short circuit faults and isolate the faulted equipment, these take other corrective actions based on specific types of phenomena such as power swings, or their oscillations or overloads. Moving to the next slide. Typically, they're deployed where you have low probability and high impact events, such as if you have a risk of overloading a line, but it is very, very low risk, where it may not justify building additional transmission lines to mitigate that issue. SPS may be installed to trip generators or trip lines to prevent the overload from causing damage, rather than investing in infrastructure. The second major case where it's deployed is unusual phenomena that are difficult to detect using other means. So this may be cases of undamped oscillations between areas, controlled system separation, controlled load shedding, and things of that nature. So these are defending the system against these unusual phenomena that really can't be tackled in other ways. Moving to the next slide. As mentioned by the previous speaker, there's a lot of different cases or scenarios where these schemes are deployed, such as overloading, frequency instability, voltage instability, control system separation. In more recent times, with a lot of wind and solar and battery inverter technologies coming on, where they connect to weak parts of the grid with low short circuit level, there are more schemes being deployed where to prevent weak grid instability, where the inverter may lose stability due to low short circuit levels. So these are becoming more common as well. The next slide, please. And again, covered by the previous speaker, there are many actions that can be taken, typically tripping transmission lines, triggering generators to run back, controlled load shedding, bypassing series capacitors, and things of that nature. Generally, and most commonly, it is tripping transmission lines or triggering generators to run back or trip. Moving to the next slide. These are just some relevant standards. You can move on 2 slides now. So I want to give some examples of deployments around the world. So the first one on the next slide, this is typical of what probably the most common type of special protection scheme deployed around the world is overload-based schemes. These are very popular now with where wind farms are connecting or solar PV farms are connecting into the grid, where there's a low risk of overloads occurring for certain grid conditions and certain grid scenarios. So in this case, there's a new wind farm connecting into the Waverley station here in the top. Now, the challenge in this area is that there's a lot of the generators in this area have been decommissioned. There was a lot of older thermal generator plants, and 65% of these have been decommissioned. And there's a lot of wind has been connected in the area with this one 130 megawatt wind farm in particular. So with these parallel lines, there's a risk of contingency overloading. And in this area, there are very high fault rates. There are many lightning storms and wind storms, which cause the lines to trip. So they installed if you wish to move to the next slide. So to mitigate these overloads or these contingency overloads, they've installed an overload protection scheme to detect overloading on these lines, but to run back the wind farm to preset levels to reduce the overload. So if you'd like to move to the next slide. So the way this operates is that it monitors the flow on each of the lines, and there are 3 stages of actions. The first is that if there is an overload of greater than 95% of the line rating, there is a run back command sent to the wind farm to decrease its power output. If the line is still overloaded after 20 seconds, the scheme actually trips up to half of the wind turbines at the wind farm site. So this is where the circuit breakers on the feeders within the wind farms are tripped at 0.25 second intervals. If after 21 seconds the overload is still existing, the entire wind farm is disconnected by tripping the high voltage circuit breaker on the grid side of the connection point. So with this, you can see how they've used multiple stages to ensure that the overload is mitigated. And if there's a failure of any one of the steps due to the command to the wind farm control system, etc., there is different layers of protection to ensure that that overload is mitigated automatically and quickly. Moving to the next slide. This is a very similar scheme in Belgium, where a large offshore wind farm was connected, 1 gigawatt offshore wind and a 2 gigawatt HVDC link. Now, in this case, there is a 380 kV line and a 150 kV line in parallel. And much like the previous example, there are contingency cases where if the 380 kV line trips, the 150 kV line might be overloaded. Now, this is very similar, but the technology used is very different in that it's such a critical line with such a large amount of power. They have a very resilient system. So they have redundant control, and they have multiple relays on each line. And they use a 2 out of 4 voting system. So at least 2 relays must recognize the overload for anything to happen. And based on the overloading, either the wind farm is tripped or the HVDC operating point is run back. So it's designed using redundant fiber links, redundant relays, redundant controllers, and the commands are all sent by goose messaging. Moving to the next example. This is probably an older example from Argentina, where they installed a defense scheme in the 90s. So in this case, there was a lot of transient stability and overload risks. They have a lot of hydropower in the northeast of the country. So there's a 3 gigawatt hydro plant and a 2 gigawatt HVDC link in this area. But most of the load is in the middle of the country around Buenos Aires, highlighted in the map. So this is a programmable logic that's implemented at the substation level with multiple logic definitions for if this contingency happens, then a generator is tripped or triggered to run back. In this case, this is a very large grid. So if those main transmission lines between the hydropower and Buenos Aires trip, there is up to 1,000 kilometers of line for the power to wheel around to reach the load. So this is a major scheme that was implemented and was actually called upon to activate 2 years ago, and I'll discuss that later. Moving to the next slide. This is just some information about how it's developed. Moving to the next slide, perhaps. Now, moving on to the more advanced schemes that are in operation now. In Guatemala and Costa Rica in Central America, they developed a synchrophaser-based centralized protection schemes. So this involves 22 phaser monitoring units installed in multiple countries in the backbone of this transmission grid. All of the PMUs measure 3-phase voltage and current, and they're measured at 30 samples per second. And these are communicated back to a central controller, to a central location, where it performs modal analysis and oscillation analysis to determine if there are any oscillations on the grid and where the oscillations were triggered or are occurring from. Based on the detection of the oscillations, the centralized scheme then commands specific lines or generators to trip offline and thus to reduce or eliminate the oscillations. So this scheme was put in place in 2013, 8 years ago, and it has been operated a number of times successfully. So this is a very modern example of wide area protection, but this required a lot of design of very highly resilient communications systems, as well as the new PMUs and the central system for determining the tripping decisions as well. So just moving to the next slide. So in this particular case, there's the system looks at the active power flowing across 2 interconnectors between El Salvador and Guatemala. It uses modal analysis then to estimate the power system oscillation mode amplitude and damping ratio. So if there's oscillations, but they are heavily damped, the system takes no action. But if there are major oscillations with large swings and they are not damped, then the system takes actions to mitigate those. It particularly looks for unstable oscillations in the 0.1 to 0.3 hertz range. The system has operated successfully many times in the last 8 years, and they've had a very positive experience. And this is as a result of spending a lot of time doing quality testing and evaluation and maintenance of the scheme to ensure that it works well. So we think this is an example of schemes that will be used quite a lot going into the future, where they're using advanced technologies and leveraging PMUs and synchrophaser schemes to deploy such an advanced scheme. Moving on to the next example, and the final example I'll give today, much like the previous one, in Iceland, they have a number of stability issues with the grid. Their grid is primarily based on a ring arrangement, which you can see in the graph in the top right here. So the most of the power is provided by hydro and geothermal generators, and they have a number of large aluminium smelting plants. So in this case, if any of the lines in the ring trip, there can be a reversal of power and significant oscillations on the system, which can lead to system collapse. So as part of this, Landsnet, the power company in Iceland, they installed a centralized wide area monitoring and protection scheme using more than 30 PMUs, and it monitors frequency, oscillation, and power flow. And if undamped oscillations or issues are identified or overload conditions, it takes actions typically within 0.3 seconds to activate fast control of thyristor-controlled aluminium smelter plants, to ramp up or down hydro and geothermal plants, to trigger load shedding, and to form microgrids with controlled islanding. So because this is a centralized scheme, it relies on very high bandwidth fiber optic communications. As I mentioned, everything occurs within 0.3 seconds. So they allow a maximum latency of about 0.1 seconds each way. So it is a very fast scheme. This scheme was begun development in 2005. So it has been around for 16 years, but they've built on it year after year after year. And they've really developed an advanced scheme that has worked very successfully for them in the past and prevented blackouts and prevented instability and other such issues. For all of these examples, I include links at the bottom so that you can click on them to find out more information. With all of these schemes, there are risks of something going wrong. So I'd like to quickly just give some examples of why it is important to put a lot of time into SIP's design to prevent failure. So just moving on 2 slides, please. So I want to give just example, you can move 1 more slide now. So just from some operating experience in the past of where issues have occurred with special protection schemes. In Norway in 2005, they have a number of system integrity protection schemes on their grid. 2 in particular, there's one in the north of the country, and for certain overloads, it trips up to 1.2 gigawatts of generators in the north of the country. There is also an SPS in the east of the country, which similarly monitors overload conditions and for certain contingencies will trip generators to prevent overloading of transmission lines. However, on the 1st of December in 2005, and you can move to the next slide, a busbar 400 kV reactor suffered a fault and a breaker failed to open, so the circuit breaker fail protection tripped the bus bar section. This caused line overloading and the north SPS to activate, but due to very slow communication systems, the command did not reach the generators in time. So this overload was allowed to persist and caused cascade tripping of a number of generators, and this led to the east, the Ostland SPS also tripping. So now the both schemes have both operated, and this resulted in almost 2.4 gigawatts of generators being lost. And this caused a significant underfrequency event and required load shedding to rebalance the grid. So this was a case where there was quite an advanced interaction between the issues, and why it's important to study their interaction. Just moving to the next example. So in Argentina in 2019, there was a scenario where there was some lines out of service for maintenance, and there was a lightning storm and a line tripped. Now, for this specific contingency, their special protection scheme should have operated to reduce generators in the north of the country. Again, you can see here in the north, there's lots of hydro plants, and in the south is the main load centers. However, the special protection scheme failed to operate, and this resulted in the power having to travel up to 1,000 kilometers in a very long route in order to get to the main load centers. This resulted in power swings, resulting in loss of synchronism and uncontrolled islanding and system collapse. Ultimately, 48 million people were blacked out, and they were restored later that day. So the scheme had been in service for many years, but there was a fault in the system which resulted in it failing to trigger for this condition. So this is why we find that it's very important to test these schemes on a regular basis and ensure that they're working as you expect them to. One more example I'll give before moving to conclusions. On the next slide, please. A similar issue. Actually, we might move on to the next slide as we're running a bit tight on time. Can we move to the next slide, please? And the next slide. So based on these design experience and considerations, you can move to the next slide now. We can see that these schemes can provide very effective means to identify abnormal system conditions, be it oscillations or overloading, and prevent them. But it's very important as part of the grid planning and operations phases to ensure that these schemes operate correctly and as expected. When they're being used in the control center, it's extremely important that there's clear guidance to the system operator on how to use the schemes, when to enable them, when to disable them, what to do if the protection scheme is out of service or a relay has failed, and how to use them in abnormal conditions like during black start or system restoration. Also visualizing and control within the control center to ensure that it presents meaningful information. A very good example was shown in the previous presentation, where it showed the status of the SPS and the operator can see exactly how it is operating. Moving to the next slide. As part of the planning process, it's very important to determine the design parameters for the scheme. What actions should it take? How quickly? When should it be enabled and disabled? Perform the necessary transient stability studies, as well as load flow and protection studies to ensure that there is no interaction between different SPS schemes on the grid, like what happened in Norway. It is also very important to consider what would happen if the defense scheme fails to operate, such as what happened in Norway and in Argentina. And also if the SIP scheme misoperates. So if it operates due to a failure of communications or human error or during maintenance, is the system resilient to all of these? And also, how flexible is the system to future system changes? So while the system is complex today, you may have more generators coming on in future. You may have more wind and solar PV farms. So is the scheme flexible that it will still behave as expected for those future changes? Moving then into the conclusions and the
excuse me,
future
Mr.
work.
McGuinness, you have
Yes.
3 minutes left.
Perfect. I'm on to my last slides. So as I mentioned, it's based on the international experience. It's very important for these schemes to be resilient to failure. So typically they're almost always now implemented using fiber optic media, especially for centralized schemes with redundant paths. And 61850 and Goose messaging is becoming pretty much the standard for all new schemes. From a redundancy perspective, historically, these schemes were implemented using a single relay or maybe one or two, but for high redundancy or high reliability schemes, we're seeing more companies move to voting schemes, such as those in Belgium, where we need at least 2 out of 3 or 2 out of 4 relays, all measuring the same conditions in order to activate the scheme. And this is to prevent incorrect operation of the scheme. Just moving on to the next slide now. So what is the future of SIPs and where are these defense schemes going? So I guess the next slide, we're seeing a lot more of these schemes being deployed. They're a growing use to support the interconnection of renewables, of wind and solar PV plants, to avoid investment in new transmission lines and to prevent uncontrolled system separation and improve the reliability of the grid. Previously, most systems were based on transmitting decisions, so trip commands or breaker status, whereas we're seeing more systems being deployed with synchrophasers, where they communicate measurements to a central location to determine the decision. This is becoming increasing in usage. We're seeing a lot more use of IEC 61850 for communications. For example, RTE in France are using dynamic line ratings. They're looking at using dynamic line ratings to dynamically change their relay loadability and relay settings in real time and to make better use of these technologies. And finally, then my conclusions on the next slide. There are many SIP schemes in operation around the world. They're increasing in number as they provide a cost-effective solution to local high-impact, low-frequency events like overloads and contingencies and oscillations. There are a very diverse range of approaches taken. There's not really a consistent practice between all companies around the world. Some use protection relays, some use programmable logic controllers, some can transmit commands or measurements. Some are centralized, some are decentralized. And we have noted a lot of cases where SIP schemes have misoperated or failed to operate. And this has resulted in under-frequency events and blackouts. So there are many lessons learned, and I would, by looking at and reviewing practices elsewhere, we can hope to avoid any repeat of these issues happening in the future. So that is my presentation for today. I covered a lot of ground, but if you have any questions, I would be very happy to answer them. Thank you very much.
Thank you very much, Mr. Sean McGuinness, for such an excellent presentation about System Integrity Protection Scheme. I can conclude some important points from your presentation. So SIPS is automatic grid protection system used to detect abnormal and designed to take corrective action other than tripping faulted component. You also deliver some practical, conventional, and modern examples about the philosophy with the complete reference below the scheme. I believe it will be a very good reference for us. We need to always update the study or contingency. We need also to test the scheme to the regular basis to make sure that the defense scheme is working well and no interaction with other defense scheme. And finally, we need to create a control center operator guideline to mitigate every probable risk. When something is happened with the defense scheme, so operator must know what to do and so on. Thank you again, Mr. Sean McGuinness, for the presentation. I believe you can see a sneak peek of the questions in the chat box. You can see it in the chat box. And I want to also remind everybody to fill in the attendance link, fill in the attendance form. Yeah, you can see, you can add the question both in the platform, in the attendance link, or directly in the chat box. Please be informed that all the question must consist to whom the question is and also your identity. For example, name and unit in PLN. And we will go to the final speaker, third speaker. The final speaker for today is Mr. Ray Doyle. Dear audience, allow me to briefly read his short biography. Ray Doyle graduated with a Bachelor of Engineering in Electronic Engineer in 1992 and joined ESB Power Generations, and he has experience as Transmission System Protection Engineer. Later, he has a responsibility of Power System Protection and Power Quality in ESB Power Generation. Then in 2006, he moved to IRGrid, and he is currently head of system integrity in IRGrid with responsibility for power system protection, protection and control, functional specification for all system developments and connections, special protection schemes, fault investigation, and other system-related responsibilities. Now let me check with him. How's it going, Mr. Ray Doyle? Mr. Ray Doyle, can you respond? Okay, I think I haven't heard your voice. Maybe the operator of this webinar can help the voice. Okay, excuse me, ladies and gentlemen, we are facing some technical problem now. Mr. Ray Doyle. Mr. Ray Doyle, I see that you haven't activated your sound to the Zoom meeting, yeah. Okay. I also see you have already 2 accounts. Can you maybe just, there's a button when we first log into Zoom, yeah, that guide us to, will we connect the sound to Wi-Fi or internet mobile or via cellular, or that? Can you see that button, Mr. Ray Doyle, before we proceed? Okay, maybe Mr. Ray Doyle, as we trying to get in corrective action to your technical problem of the voice, you can keep on trying to connect to sound, and the committee will also think of several procedure to revive this. I think we can go first to the Q&A session. And we will go when we are joined with us, we can go back to you. First, let's see what is in here in this question list. Let me open the question sheet. Okay, I have this question by Mr. Antonius Danang from PLN Pusat. The question go to Pak Daniel, PLN Kalimantan. Yeah. The question is there any blackout system occurred after the implementation of SPS in Katulistiwa system and Kalimantan system? And what was the blackout caused? Yeah. Okay, Pak Daniel,
Haryadi,
can you connect?
Sorry, could you please?
Yes, I can repeat the answer, the question.
Yeah, repeat the question.
The question from Pak Antonius Danang: is there any blackout system occurred after the implementation of SPS in Katulistiwa system or in Kalimantan system? Yeah. What was the blackout cause, and what about the performance of the defense scheme? Yeah, you can answer.
Okay, Pak Hadi. Okay, thank you, Pak Danang, for the question. After installation of the first SPS in Kalimantan Barat, we have experienced after that the blackout. Sorry, not blackout. The trip of the transmission line from SESCO twice. The occurrence, and because of SPS already installed, the system can immediately back to normal. As I state in the slide number 16, yeah, slide number 16, state on the right, after installation of SPS in April and May 2017, then in October 2017, the same condition happened. The tie line from Mambong Bengkayang and Singkawang Bengkayang trips, and at that time we have transfer from SESCO, and then the SPS successfully prevents such blackout, because the SPS is already calculated the megawatt feeder to be prepared according to the megawatt transfer from SESCO. So every 10 seconds, the system calculated, let's say if the transfer 100 megawatt, the feeder to be prepared also selected to equal to the 100 megawatt dynamically. Occurrence, we can avoid such blackout. So based on this experience, we are confirm that the system can working properly, but also so many opportunity for improvement for the system. We still learn about the system and improve time by time. Thank you, Pak Haryadi.
Thank you, Pak Daniel, for the answer. Okay, ladies and gentlemen, I want to try to reach once again to Mr. Ray Doyle. I think I have some suggestion about how we can reach you. Yeah, first is we can try you to dial the Wi-Fi, the join audio button in the bottom left in Zoom application, both in PC or in the smartphone, and you can click Wi-Fi or cellular data, yeah, to there. But if we cannot join you in that way, maybe I have to ask Mr. Sean or Mr. Mark McGonagall if it's not maybe. So maybe you can dial by phone in the same local telephone, yeah, and we can put that sound from your account here. Yeah, if we go back to the answer from Mr. Daniel. So let me open this first. So the question is from Antonius Danang. If you have some other remark or question, you can directly unmute the mic, maybe. Okay, then we will go to the second question. Second question is to Mr. Sean McGuinness. Mr. Sean, can you copy me?
Yes, I can hear you.
Okay, the question is from Pak Komang from RJT, from Transmission Regional of PLN Head Office. The question is what we need to improve to build defense scheme with the high load interconnection without touching the safety net. I mean, without no load being shed. Do you have some experience to it?
It depends on the nature of the disturbance, I guess. If it's purely to mitigate overloads, nobody wants to trip load, but unfortunately, if there's a frequency imbalance, that may be the only output that can happen. Depending on the nature of the overload, when you overload a line, it normally takes at least several minutes for the conductor to heat up and to sag down like this. So you have a number of minutes to make a response. In some cases, you may be able to bring a generator online, particularly if you have a hydro plant, which are capable of ramping their power output very quickly. If you have those available, or if you have pumped storage or battery banks, which can respond very quickly, it's possible to put those in place to quickly ramp up their power or absorb power and use those to mitigate the overload instead. But if you do not have those resources available, then unfortunately load shedding it may be the only way to go. In some cases, you can trip generators to reduce the overload in a local area. And in EirGrid in Ireland, they implemented such a scheme before, where they had line overloading in a particular area. If the loading persisted, it would cause the generators to run back. If you have a frequency stability problem, however, then you will typically have to rely on hydropower plants, pump storage, or battery energy storage to quickly mitigate the overload. I hope that answered the question usefully.
Yeah, we can understand it. But the interesting point for me, I think we in PLN are not having the rating, the timely rating. Like in your presentation, you showed us that if the loading of the transmission lines is exceeding 95%, you have like 20 seconds and also 50 seconds and so on to mitigate it. But we don't really use that standard in PLN, and maybe we can try to learn from you. Yeah, maybe this is in this tropical area. We have some sagging. It will be some much burden to the transmission asset. Yeah. But your idea is very understandable. Yeah, we have some corrective action with that palm start and so on. Yeah, but the difficulties in PLN is we must mitigate that as soon as possible. Yeah, we don't have some timely delay like yours.
Yeah.
Thank you. Do you have something to add?
No, just to mention that in South Australia, they have a large battery bank. I think it's about 100 megawatts, and that has been used quite extensively to mitigate frequency disturbances very quickly. And indeed, it has responded to overloads on the interconnector between South Australia and the main Australian grid for exactly that scenario. And it responds within 100 milliseconds. So that this is, if very fast response is necessary, there are those types of solutions as well. Also, if you have wind farms and you have them curtailed, so if you have a 100 megawatt wind farm, but for some reason it's operating at 80 megawatts, to prevent contingency overload, you can release that 20 megawatts of spare headroom. So this is done in other countries where they allow the wind farms to provide frequency response as well. So this can help in some cases.
Okay, thank you to Mr. Sean McGuinness. So as we're trying to reach Mr. Ray Doyle, let me continue to have some question to Pak Daniel first. The next question is from Michael, PLN UIKL Sulawesi. Ya. Just go to Pak Daniel. So there is SPS dynamic and static in SPS system interconnection design. What is the difference between the model when we use the static or when we use the dynamic? Yeah? What is the position between both of them?
Okay, yeah. Thank you, Pak Haryadi. Pak Michael from PLN Sulawesi. SPS relays by default position in dynamic mode, and in position into static mode if the SPS server is not working because of equipment out of service or under maintenance. When in the static mode, the system works on the principle of direct transfer trip. This means that in the future we will develop the automatic detection like self-check of the system. If there's something error in the hardware, the system can auto change over to static mode. But this time, the existing SPS we have in Kalimantan Barat, the system is still in a manual mode. That means need personnel to check if the hardware is working or not. So at this time, we still manual to switch between dynamic default position to static if there is something error in hardware. That's all, Pak Haryadi.
Thank you, Pak Daniel. Okay, next question, we will go to Mr. Sean McGuinness.
Sorry, Pak Haryadi, Mr. Ray Doyle, raise hand, maybe.
Hello.
Okay,
me?
Mr. Ray Doyle, can you hear us?
I can hear you, yes.
Ah, finally.
Can you hear me?
Yes, I can hear you now, Mr. Ray Doyle.
Okay. Sorry
Okay.
about this.
Okay, so it is very, I'm very glad to have you join with us today, although there are some technical issues now, but it is okay now. Let me introduce Mr. Ray Doyle, ladies and gentlemen. Okay, please wait a minute. Okay, let's go to our final speaker presentation for today. Allow me to briefly read his short biography. So, Mr. Ray Doyle is graduated with a Bachelor of Engineering in Electronic Engineer in ESB Power Generation, yeah, and you moved to EirGrid in 2006. Now you are head of system integrity in IRGrid with responsibility for power system protection and control, and so on. So, Mr. Ray Doyle, thank you for joining. You have 25 minutes, and the presentation material will be presented. Now the time is yours.
Okay, look, good morning, everybody. Sorry about all the technical difficulties I'm having here. So, look, we'll get straight into it. So, go on to the next slide, please.
Next slide, please, operator.
Okay, so this morning I'd like to talk to you briefly about, I suppose, the changing nature of the Irish power system, our new approach to the treatment of transmission and distribution system interfaces, special protection schemes that we have deployed for slave tripping and anti-islanding, so we're shutting down island systems, mitigation measures we have in place for the loss of interconnection, and briefly on temporary SPS for network management. So next slide, please. Okay, so on the Irish power system, so the level of renewables renewable energy have increased significantly. We're currently operating the system. We're currently operating our system with up to 75% non-synchronous sources. That's currently, it's primarily wind energy and HVDC interconnections currently, and we will, over the next number of years, we will be connecting a lot of solar energy to our system. I suppose the other major change is that the generation portfolio is changing from a small number of large conventional plants to connected at transmission level to large numbers of small capacity sources connected both at transmission level and at distribution level. Okay, so next slide, please. Yeah, so I suppose this change poses a number of challenges for power system protection. Namely, we've got bidirectional power flows at transmission and distribution interfaces, lower fault levels at times of high non-synchronous generation penetration. So when all the conventional plant is displaced, it's basically replaced with wind farms or HVDC interconnection. Fault-induced voltage dips, again, when the system is weak, or if we do get a short circuit fault, the voltage dip impacts over large areas. Again, due to the nature of our system, we've got a higher probability of islanding stations or section of network. So at the 110 kV system, where a lot of the renewable generation is connected, we have a lot of two-line stations, so risk of islanding is quite high. And then the other major challenge for us is basically lower inertia, again, with displacement of conventional plant with renewable generation. Okay, so next slide, please. So I suppose here, just looking at a classical transmission distribution interface, and so if we get a fault on the HV side of a distribution transformer, all the power flow is from the grid. So just, can you advance the slide? There's some animation on this, hopefully it works. Okay, can you try and advance slide? Yeah, super. So yeah, so if we have a fault on the HV side of a distribution connected or a transmission connected distribution transformer, basically the power flow basically is from the transmission system to this transformer. Okay, advance please, next slide. Yeah, so, and go one more please. Yeah, so again, if the fault is on the MV side, it's the same thing, all power flow is coming from the from the transmission system. And go again, please. Go. And one more. Yeah, so similarly, the fault is down in the MV system. All power is flowing from the transmission system through the transformer through the MV network. Okay, next slide, please. And so now, if we have a fault on the transmission system itself, basically the sources of power or short circuit are from some other part of the system. So there's no contribution from the distribution system where there's no generation connected. So move on to the next slide, please. Okay, so our traditional approach traditional TSO approach at demand interfaces, so the passive load with no material contribution from the transmission system faults. So we typically deployed two-stage HV side overcurrent protection, stage one with a low set definite time for clearing LV side faults, and stage two, high set instantaneous for LV side faults. So next slide, please. Yes, our criteria for setting these things is stage one must operate for LV faults under all feasible network conditions. Stage two must not operate for LV faults at times of max short circuit strength. Stage two must operate for HV side faults at times of minimum system strength. Again, because of the changing nature of the system, criteria 2 and 3 can conflict when we've got weak power system and large transformers. Okay, so next slide, please. Yeah, so typically, you can see there on the HV side, we would have fitted overcurrent protection. That would have dealt, so stage one would have dealt with the fault on the MV system. Next slide, please. In the instantaneous, stage two would have dealt with faults on the high voltage side of the transformer. Okay, so next slide, please. And go again, maybe. Sorry, advance again, yeah. Yeah, so what we've got now, so in the modern setup, where there's basically both load and generation connected on the distribution system. So now, if there's a fault in the distribution system, obviously there's contributions from the transmission system, which you can see coming from the left, and there's also now contributions from the distribution connected generation resources. So obviously this impacts now on our traditional overcurrent protection installed on the HV side. So next slide, please. Okay, so now we're showing a fault on the transmission system itself. And so advance one more, please. Yeah, so now we've got contributions coming from the distribution system, which we didn't have in the past. And so our protection was not basically set up to deal with this. So our current approach now is basically, as the TSO-DSO interface serves a mix of generation and load, we could have contributions from the LV side through HV busbar faults and HV feeder faults. So the transformer may need to be tripped by non-unit type protection to clear HV busbar faults or HV feeder faults in the event of feeder protection or circuit breaker failure. Okay, so move on to the next slide, please. Okay, so what we're doing now at interfaces, on new interfaces, and we're also retrofitting this to existing interfaces. So we're putting distance protection on the HV side of the transformer, which requires 110 kV VTs, 110 kV side VTs, which typically would not have been installed. So we're basically, where we have CTs only, we're replacing them with combined CT-VT units. So this is used to protect the system from faults on the connected plant, and it also provides backup protection for LV and HV busbars and for HV feeders. And I suppose the good thing about this is the operation is largely independent of system fault level. We just need to exceed a minimum current detection minimum current for fault detection, which can be set lower than load current levels, which was not the case previously. Okay, next slide, please. Yeah, so we've started fitting, as you can see there, current transformers and voltage transformers, distance protection, and voltage and frequency protection. And you can see there the distance relays are set typically with first step forward 80% into the transformer, second step is looking 100% looking into the MV bus bar, third forward step is looking maybe 150% looking down into the distribution network. Then looking the other direction back towards the HV bus bar, so we have first step set at maybe 80% of the shortest feeder connected to the transmission station. Okay, next slide, please. So just I want to talk briefly about measures we put in to deal with anti-islanding and slave tripping. So just showing a small section of 110 kV network here. So we have, multiple 2-line stations in a row. So during maintenance combinations, or if 2 lines were to trip together, various stations can become disconnected from the transmission system, and so they can become disconnected now with local generation. So our strategy here is basically to put in schemes to try and shut these islands down quickly if they form. So move on to the next slide, please. Yeah, so with this arrangement, there's increased risk of sustained islanding situations following system disturbances. Voltage and frequency can come out of control because bits of the network no longer connected to the main system, and there's plant potentially operating outside normal operating ranges, so voltage and frequency can be out of normal operating range. And this is dealt with by anti-islanding or slave trip special protection schemes. Okay, so next slide, please. Yeah, so to do this, the second relay fitted at the interfaces or at TSO IPP interfaces to provide voltage, frequency, and other SPS functionalities. So position indication of HV breakers is also used as triggers, so that's fed into the relay. And where fast-acting slave tripping is implied to shut down, where feasible, fast-acting slave tripping is implied to shut down island and network or node. Where this is not feasible, then under and over voltage and under over frequency functionality is relied on to shut down islands, which is obviously slower acting because it's more difficult to distinguish between maybe a fault in the system and basically a genuine islanding event. Okay, so if you go on to the next slide, please. Yeah, so here's just some data from fault recording showing basically what happens basically when an independent power producer transformer becomes isolated from the network. So in this case, it's a wind farm. At minus 50 milliseconds, basically the installations become islanded from the system. 22 milliseconds later, the voltage has gone up to 150 kV at the disconnected site, and the frequency has gone to over 60 hertz. Then the over frequency SPS disconnected this, you can see there. So it's in about 150 milliseconds, it's been disconnected and shut down. So next slide, please. So I suppose this, just advance one more, please. Yeah, so we're showing here, so we've got on the right-hand side a piece of tail-fed network, and basically the breaker back at the source end of the line has opened. So basically, slave trip is sent to the breaker at the remote end. So next slide, please. Yes, that slave trip basically opens the breaker. Okay, so Just very quickly how we're doing this, basically on the right hand side, the circuit breaker status is fed into a binary input, basically on the protection relay. So there's also a check to make sure the DC supply is healthy, so they're into an AND condition. So then there's some enable disable logic, so that can be turned on, enabled or disabled either locally in the station or remotely from the station or from the system control center. And then basically, so if the breaker opens and the DC is healthy and the scheme is enabled, pulse is sent via the teleprotection to the remote end. Then that's picked up at the teleprotection interface at the remote end and fed into the relay again. So again, if the DC supply is healthy, the receipt of that signal, it goes into the enable disable logic, and again it's into a pulse timer. And so if it's enabled, basically the trip contacts are commanded momentarily to open the breakers. So that's just one example of how it's actually implemented. Okay, so next slide, please. So here we're showing we've got a fault basically on the feeder itself. So the feeder's protection will open both ends of this feeder. So if you just go to the next slide, please. Yeah, so basically now, the breaker at the remote end tailfed station has opened because of a feeder fault. Again, that change in status of the breaker is picked up, and basically it's then relayed to the other breakers, basically connecting the generation and load transformer. So obviously the point to make there is the loss of the tail feeder basically is creating island. Sorry, can you go back one slide? Go back one more. Yeah, so here, so the fault on the feed on the tail feeder basically has islanded generation here. And so then the open breaker status is used basically to open the breaker on the generator and on the load. So basically opening all breakers and shutting down the island. Okay, we'll move on to the next slide. So here, basically, again, we're showing basically 3 two-line stations in a row, stations A, B, and C. And so here we're showing an example of fast-acting islanding. So basically, the 2 lines into station B are going to trip islanding station B. So if you can advance one, next slide. Okay, so the breaker has opened at station B, and that's going to slave trip its partner breaker at station B. Now, station B is still connected. So now the line to station C is going to trip. So if you just advance, next slide, please. Yeah, so the breaker at station C is shown open there, so that's going to slave trip its partner breaker at station B. Okay, so next slide, please. So now, yeah, so the 2 local breakers in station B now have been slave tripped. So now there's basically islanded generation at station B. So the islanding scheme basically detects that the 2 main line breakers are now open, then moves to shut down that island. So if you just, next slide, please. Yeah, so it sees that both breakers are open, and then slave trips are issued to the 2 breakers. Okay, so next slide.
Excuse me,
okay,
Mr. Ray Doyle. You have 5 minutes left.
Okay, thank you.
Okay.
Okay, so next slide, please. So this is an example of the slow acting one. So basically, you know, so the line, one of the lines into station A has tripped, and one of the lines into station C have tripped. So now basically, essentially stations A, B, and C are actually islanded, but we're not able to get the breaker status from the necessary remote ends. So now we're relying on voltage and frequency protection to kick in. So there's an island, there's islanded generation there in 3 stations. So voltage and frequency protection is active. So next slide, please. So that operates to open the generation at the 3 sites, basically, so shutting down these islanded networks. Okay, so next slide, please. Okay, so just running out of time, but very briefly, how we deal with loss of interconnection. So the island of Ireland basically is interconnected with the UK via the East-West interconnector, and Northern Ireland is interconnected to Scotland via the Mile interconnector. So next slide, please. So I suppose the challenges here. So if we lose basically interconnector import, we're left with basically a deficit of power on the island. So that leads to low frequency. That's dealt with the normal governing reserve and maybe tripping load on load shedding if we need to do it. I suppose the new problem we have with interconnection is basically the loss of exports leading to high frequency. This is dealt with by reducing or tripping generation. So it depends on the circumstances. This can be wind generation or a conventional plant. So next slide, please. Yeah, so exports on our system on the interconnectors typically occur at times of high wind generation. So we have minimum number of conventional plant on, we've got low system inertia, and the loss of large exports can result in rapid increase in system frequency, which quickly needs to be arrested. So next slide, please. Okay, so to manage this, so it requires fast reaction on the remaining interconnector if capacity is available. So to either increase export if that's possible, or fast reduction of conventional plants if operating above their minimum generation levels or tripping them. So negative reserve is held at times on conventional plants for this reason. And then either the fast reduction or the tripping of wind generation. Okay, next slide, please. So here's basically what will happen in our system, basically, if we lose a large export and we don't take corrective action. So we'll go from 50 up to 51 hertz rapidly in a matter of maybe 1 or 2 seconds. Advance to the next slide. Yeah, so basically, so the yellow trace there shows basically what happens when we have what we call our over frequency generation shedding in operation. So basically, it's arresting the rise at about 50.4 hertz, and then bringing it back down to normal over maybe a 15 or 20 second time period. Okay, next slide, please. So our conventional run back scheme. So in this scheme, we have 3 combined cycle plants that are involved in this. So, and we've got frequency monitoring at central location. So we can send commands to each of 3 stations to reduce power, or if it's too quick, if we need to get rid of it quickly, we can trip the selected ones off, trip selected generators off the system. Next slide, please. Yeah, so this is just a view in the control center. So it's probably difficult to see it, but down the bottom, the green buttons there is the scheme status, so whether they're on or off. In the middle, basically we can send, so if we're using runbacks, we can put in set points, so these would be set up in advance. So we can automatically have the set points that the machine is to run back programmed into. Then in the event of a loss of interconnector export, this can be triggered to run back to that level. Or we can also opt basically to trip the machines, so not wait for them to run back. Okay, next slide, please.
Okay, Mr. Ray Doyle, we have 1 minute left.
Yep, 1 minute. Okay, almost there. So the over frequency tripping of wind generation, basically, so we can select wind farms We are keeping a total negative reserve of 550 megawatts, which is the max import on the max export on the interconnector. And the wind farms are then tripped on 3 separate tranches of over frequency, so 50.32, 50.37, 50.42. And so there's no intentional delays set on these. Okay, next slide, please. Yeah, so this is a real example of loss of export on interconnector. So at time 0 there, you can see that system frequency is shooting up to 50.4 hertz, and obviously we're activating the tripping of wind farms and the run back, so the rise is arrested there at about 50.4 hertz and brought back down within 10 seconds down to 50.1 hertz. Then operators take over with manual interventions. Okay, next slide.
Okay.
So then simply SPS for network management. So I suppose the drivers here, trying to facilitate renewable generation and minimize constraints on the network in advance of the delivery of new and upgraded network infrastructure. So it's much quicker to build generation connections than basically to build the transmission reinforcement. So we're putting in basically various special protection schemes to deal with issues in the time between connection of generation and the necessary transmission system reinforcement. So they're a combination of overload SPSs, looking at contingencies deep in the network and issuing either trips or runbacks to generation, and then over voltage
Yes.
for controlling system voltage in advance of having STATCOMs and reactors. And I suppose, as alluded to earlier, this is all resulting in ever increasing operational complexity and the need for all sorts of guidance for control centers and a lot of work, managing outages and managing complex situations. So I suppose all of this is making the operation of the network much more complex and more prone to errors. So I think that's my last slide. So let's just move on. Yeah, and this is just an overview. So here we've got it's just a single line diagram of the network, and all those places you see there with red, yellow, and blue dots are locations where special protection schemes of one variant or another have been deployed. It's quite hard to see this, but you can see there's on the yellow ones, there's arrows from one station to another. So basically, at the source station, we're monitoring some quantity, whether it's voltage, frequency, or load, and then the action is taking place at the station at the other end of that arrow. Okay, I'll leave it at that. We're out of time. Happy to take questions.
Okay, thank you, Mr. Ray Doyle, for your presentation. It's quite technical, yeah, quite technical. So it will be a very good reference for us in PLN. For the question, I would like to give the opportunity from the PLN management for asking the question directly to the speaker. In this session, I'd like to have Pak Ahmad Murdani from PLN UIP 2B to ask the question directly to the speaker. Pak Ahmad Murdani, do you copy?
Good afternoon, Pak Haryadi.
Good afternoon, Pak Ahmad Murdani. Thank you for joining with us. You can ask the question.
My question is for Ray Doyle, Mr. Ray. Actually, I have two questions regarding the lower inertia system and also the islanding scheme that he already explained before. First, you said that in your presentation about you have a lower system inertia. In terms of that mitigation to that phenomena, what are the mitigations that you use to solve this problem? Are you pushing the existing synchronous generator to reset the rock-off protection, or you push the inverter-based generation to what we call introduce the synthetic inertia, and how is the enforcement? This is the first question. And the second question, and do you mind if I continue with the second question, or like to answer?
Ask the question.
The second question is about the islanding system that you already explained before. That how, as we know that the islanding systems works properly and successfully if there is a balance between active power and also reactive power. And as we know that systems, in your system as well, changing over time, like minutes to minutes. And how do you then ensure that your island system or island mechanisms protection scheme work properly or successfully? Is there any special mechanism in initial conditions that you have to ensure your island works successfully? That's all, Mr. Ray. Thank you very much.
Okay, so the first question on the inertia. So I suppose, so we have changed our system to allow rock off of up to 1 hertz per second. So all the rock off settings basically have been increased up to 1 hertz per second on distribution connected generation. Now we don't employ rock off protection on the transmission system, but all the rock-off relays have been set up to 1 hertz on distribution connected generation. And so also in the control center, we keep track of the conventional plant that's on the system. So we keep track of their inertias. So we operate a minimum amount of inertia. So we always make sure that there's sufficient inertia on the system, basically to maintain the rock off within 1 hertz per second. So that sometimes requires us to constrain on conventional plant. Maybe that wouldn't otherwise be needed. So sometimes we would have to constrain wind power, basically, so that there's space for sufficient conventional plant on the system, basically to maintain a minimum inertia level. So the control system, like the energy management system, is keeping track of the inertia in real time based on the status, basically, of all the connected generation. And again, so we maintain enough conventional plant on the system to maintain rock off less than 1 hertz per second. So hopefully that answers that question. Then on the second questioning about islanding networks, so I suppose we don't try to maintain the island. So our strategy is, if something becomes islanded, is to shut it down immediately. So we either do that so we can do that quickly if we have the status of enough, the surrounding breakers to know that something has become islanded. And if that's not the case, then we're relying on voltage and frequency, basically to detect voltage or frequency conditions out of normal range. So I suppose in most of our locations where this is an issue, like there isn't a balance between demand and generation. Usually the generation is way in excess of the system demand. So that usually, if we do have an islanding event, it usually results rapidly in very high frequency. So we're not actually trying to keep them live. Our strategy is to shut them down. Then once they're shut down, we'll put the network back together and reconnect in a manual fashion as quick as can be done by the control center. So let me know if that answers your question.
Okay, thank you, Mr. Ray Doyle, for your answer. We understand that. We have 2 questions in a similar way, from Mr. Mark McGranagan, and it is similar with a question from Rahman, from UIKL Kalimantan. So what actually, you can answer this briefly, what actually the protocol that you are using for the protection scheme? Is this the GUS messaging or something else that use master slave stripping signal or something else?
Sorry, can you repeat? I just got part of that about the protocol we were using for which, but I'm not sure what.
Yeah.
What you're actually asking.
So the question is IRGrid using Goose messaging for the SPS implementation? Yeah, that's the.
No, we're not using Goose messaging. Basically, we use basically dedicated teleprotection channels. So, just on the we have, I suppose, a reasonably extensive fiber optic network on the system at the moment. So basically, we're using basically teleprotection interfaces, basically to relay breaker status from one station to another. So we're not using Goose messaging.
Okay, thank you, Mr. Redoyel. Thank you also for your answer. I might go to Mr. Sean McGuinness first. There is a question from David, Unit Induk Transmisi JBM. The question is for Sean, which one is better, to have the SPS relays in the substation or in the control center regarding the overload sending trip signal? Yeah, regarding the sending trip signal.
Thank you. This is a very good question. It is possible to implement these overload schemes using SCADA on your EMS. You can implement automatic switching sequences if overloads are detected. However, this requires very reliable communication systems to ensure that the measurement gets to your EMS. It's a reliable measurement, it's accurate, and that the relevant tripping commands get to where they need to go. However, if you implement those customized sequences in your EMS, it can sometimes be challenging to maintain them and also to migrate them if you're upgrading your EMS. So if you have an EMS product today and you're updating it or you're replacing it with a different vendor in future, it can be very challenging to migrate that over. So for these reasons, it has been pretty common that most transmission system operators prefer to implement the schemes in the substation, as it removes a lot of the risk associated with the communication schemes and the EMS dependency. I hope that answers the question.
Okay, thank you, Mr. Sean McGuinness. I might go again to Pak Daniel. Pak Daniel, yeah? Do you copy, Pak Daniel?
Yes, please.
Okay. Thank you. There's a question from Jainul Arifin, the Kantor Pusat. So, how could the SPS adapt the changes of Kalimantan system if there is the new addition of generation or transmission line? Yeah. So, how could that adapt?
Okay, thank you, Pak Haryadi. Thank you, Pak Zainul. Good question. As I explained in our presentation, that we have additional more SPS installed in interconnection system, which is the system is growing up with additional new substation. We have to be careful and periodically review our SPS system, and the contingency we select, as I explained in the previous slide, that we have some contingency, the scenario, what scenario to be created and to anticipate. So that's in technically we have to adjust our design according to system development. Maybe my answer can satisfy your question, Pak Jainul.
Okay.
Yeah.
Thank you, Pak Daniel, for the answers. Yeah. We should go, yeah, because to remind of the time. Yeah, we are going to the last question. Yeah, the open mic question from Joko Hartono. Do you copy with us, Joko Hartono? You can ask some quick, brief question. Yeah.
Yeah, thank you for the opportunity. I want to ask one question for Mr. Xian. From your explanation, SAPS is working for the event that historically repeat or plan, then store on the database as the decision action. So how SAPS works to anticipate the event that actually first time incident or not planned? That's my question. Thank you.
So if I heard the question correctly, is that how does the SPS scheme respond to new events that haven't been seen before? Is that correct?
Yeah, that's correct.
Okay. Typically with the schemes that have been designed, they try to catch as many cases as possible during the design and planning stage. Unfortunately, like you mentioned, there can be unusual events that haven't happened before, such as the one in Norway that I mentioned, where you had two SPS that interacted because there was slow communications. That was not expected. It was a new event. And unfortunately, for those types of events, they're very hard to predict what can go wrong. And I'm not aware of any scheme or design to allow total flexibility and resilient response. But I guess the big thing is that, when you're doing, you know your grid, you understand your grid, and to try and study as many credible scenarios at the planning stage is the best way to design the resilient system. That's pretty much all you can do, and ensure that the communications and the relays are reliable and redundant to prevent failure. So unfortunately, there's no magic answer to that, apart from doing your homework and doing as much studies at the planning stage.
Okay, thank you, Mr. Sam McGuinness and Mr. Joko Hartono. Unfortunately, I have to remind all of you because of the time. And ladies and gentlemen, we finally come to this end of this Q&A session and the panel presentation session. Before I close the webinar, I would like to take several conclusions from what the speaker was presented. So for the system integrity protection scheme is automatic grid protection system used to detect abnormal and predetermined system condition like power swing, and designed to take corrective action other than tripping faulted component. Several cases of SIPS missed operating or failed to operate, like or in wide area protection schemes in Argentina, and other examples due to the slow communication, human error during maintenance, or the not sufficient guideline to the operator. It is have to be improved well. Yeah. Also, designing a smart protection scheme must consider system operation, system planning, and a resilience to failure. Also, there's a lot of technical examples from Mr. Ray Doyle. Thank you for that sharing. It is very good for us to have our bigger understanding about the scheme in the defense scheme around the world. Finally, I'd like to thank the speakers from PLN, from EPRI and IRGrid for informative and fruitful presentation, especially for GPST that makes this happen. I also want to thank all of the audience to the very active participation. Finally, please join me to give a big applause for the remarkable speakers and for you all. Thank you very much for joining this webinar. I'll pass the platform to the beautiful Master of Ceremony, Mbak Farika. Thank you very much.
Thank you very much for Mr. Daniel, Mr. Sean, Mr. Rai, and also Mr. Haryadi as the moderator for the wonderful sharing. Ladies and gentlemen, this is maybe our last session of the 4th Power System series, but please stay tuned until the closing session today because we have fun quiz before the closing remarks. So please be ready because it will start in about 5 minutes. For all the participants, please grab your second device and go to the link or type the code shown on our screen. Menti.com and retype the code of 48904940. Kindly please type your real name as the identity to simplify the committee for the prizes claim. I will wait until 5 minutes ahead to get it started. It's already 37, 38, 40 participants here in Menti.com. Tomorrow you will touch until 100, 50 or 100%. Oh, it's about 60. Okay, I will wait until it's touch 100% in this room and we will start the quiz. 64. Okay. So the committee, can we start it right now? Or until wait until it touch 100 participants? It's right now 76 participants here. $80 participants. $85 participants. It's wonderful. It's already 4 p.m. here, and there are a lot of participants still staying until the quiz sessions. Okay, I will wait until 100 participants. Right now is 90 participants. $94 participants, 6% to go. Six participants, 4% to go. We have a very interesting prizes for the person that the winner in this quiz session, and also we have best questions to be announced later. To go, touch your room and touch your ticket. Okay, let's get started. Time is up and I will start the quiz right now. And 1-1 reiteration, interconnection load between Sarawak and West Kalimantan is limited to. For option questions, 80 megawatts, 110 megawatts, time's up. Wow. get best answer, please kindly type your real name or your real identity to make our committee easily for prize claim. Question 2 of 10. Please be prepared. The event of a power outage that underlies the idea of implementing SPS in the Katulistiwa power grid occurred in I hope that Mr. Daniel doesn't join this quiz because he will be a winner, I think. Okay, we have still have Mr. Israjuddin as the leader for the second quiz. Now we are going to the third quiz. Transmission disturbance in Kalimantan interconnection grid are dominated by head wire, trees, lightning disturbance, and confinement cable. 4, 5, 3, 2, 1, thumbs up. Right answer, lightning disturbance. Who is the right answer and who is got the right answer? Still we have Mr. Israjuddin as the winner. And also the fastest. Okay, we are going to the fourth question. For monitoring and visualization of the SPS system, Talent Kalimantan use the platform You have 5 seconds to go to answer the question. Now, Mr. Tesla Flow. What does SPS stand for? Okay, the answer right question is Special Protection Scheme. Question number 6 of 10 questions. Two of those problems does an SPS not typically solve? Time's up. Here that very competitive. Here they are, Tesla Flow and Mr. Israjuddin. Mr. Tesla Flow, can you please retype your identity? You need a Spirit ID system to manage SPS. of 10 questions. Up to 8% of non-synchronous power sources that Air Grid currently operates the IRIS power system. %46 are doing answer the wrong. So for the winner of this quiz, please contact the committee after the quiz session was end. And please give the screenshot of your identity for this session. We're going to have the last question after this. So this is the last question. What is one of the main disadvantages of deploying special protection scheme? Here they are, the winners. Going to Mr. Tesla Flow. Please contact to the committee and give your real identity to prizes claim. Congratulations for all the winners. And also for the next session, we would have to congratulate from the best question session. So congratulations. Here they are. Mr. Michael, Mr. David, and Mr. Rahman. Congratulations. And please contact our committee for the prizes via chat box. We'll have interesting prizes for you all, and we're very thankful for your good cooperation and also your enthusiasm in this quiz session. And here we are, proceed to our last agenda. Please welcome Mr. Heri Nugraha as the 4th Power System Sharing Series host to deliver the closing remarks.
Thank you. Okay, I would like to make a closing speech. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera untuk kita semua. Salam, Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Good afternoon to all participants. Thank you for being actively involved in this webinar. As the meeting host, allow me to express my best gratitude to all honorable guests and speakers. Thank you to Mr. Nur Wahyu Dinianto, Mr. Mark McGrahnakhan, Mr. Sean McGuinness, Mr. Ray Doyle, and also Mr. Daniel Eliawardana. Thank you for the knowledge you have shared during the webinar. Thank you also to all audiences for your time and attention. We hope all of you enjoy the seminar and obtain the more excellent knowledge regarding the Smart Defense Scheme. Thank you to our MC, Ms. Farita Himawati, and our moderator, Mr. Haryadi Adi. Thank you also to all colleagues from the PLN Corporate University and the P2B who prepared the webinar. See you again in the next webinar of PLN GPST Consortium. Success to all of us. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Salam Om Santi Santi Om. Namo Buddhaya. Salam kebajikan. Thank you very much.
Thank you very much, Mr. Heri Nugraha, for the closing remarks. Ladies and gentlemen, this marks is the end of the 4th Power Systems Sharing Series. We hope that this sharing session can give us a remarkable lesson learned for the next development and implementation of power system stability. And please allow me to give you one pantun like usual. Jalan-jalan naik kereta, tamasya di Irlandia. Mari berkarya dan bekerja untuk PLN semakin jaya. Thank you very much for your participation and your attention. As the master ceremony today, representing the committee of the event, let me apologize for any lack of this event. See you on the next Power System Sharing Series. Have a blessed day.
Thank you.
Thank you, Sean. Thank you, Ray. Haryadi.
Kepada Daniel.